So the LLama3 large language models use an architecture resembling this, what I drew out on the board. The first step is to convert some raw text you give it into a format that's familiar to it. Like, for example, when we're reading a book, we expect there to be structured sentences and paragraphs, and in that case we would add indents for the paragraphs. So first we apply something called a chat template, which puts the raw text into a format that the large language model would recognize. Then, after we process the raw text into some more familiar text, we have to compress it so that we can work with it a lot better down the line. That's because for each number we give this large language model, we have to do this much processing. And just imagine how inefficient it would be. Just imagine how inefficient it would be to have to spell out every single word as you read it. We don't read individual letters, we read words or phrases as a whole. And tokenization takes in the raw text, the letters we have, and merges it together into whole words. Therefore, we eliminate the complexity of the text. All we have left is a bunch of phrases and words instead of the original characters and letters we had. So we only have to process one number for each word instead of 10 numbers for each character. So that's what tokenization serves. And what we get out of that is a set of numbers called tokens. Now, after we have these tokens, we still can't work with them very freely because a single number can't really encapsulate all the meaning of a word. For example, we may have the word cat. Now, the word cat incorporates the fact that it's a mammal, the fact that it has 4 legs, and it has fur. And all of these attributes can't really be represented by one single number. So what we have to do is we have to take this number and expand it out into multiple numbers which capture the meaning of the word. And this is called embedding. When we take our token, which is one number, and we expand it out into multiple numbers, and a set of multiple numbers is called a vector. So that's embedding. Now, after we have these vectors, they may be of all sorts of different sizes because a vector is not just a set of numbers, but it can also represent a direction, the same way how if we have 2 numbers, we can take them as a coordinate, the coordinate system. Now that's a direction from the origin. Here, if we have lots of numbers, we can think of it as all of those numbers representing a coordinate, some sort of higher dimensional coordinate system, and they represent a direction in that coordinate system. And so the best way to think about these vectors is actually not just a set of numbers, but a direction, an arrow, if you will, in a large coordinate space. And these arrows can be of many different sizes and be centered at many different places. And that's not good, because what happens is that as soon as we start adding and multiplying the numbers inside of these vectors, one of 2 things can happen to these vectors. They may start growing, and if they grow a tiny bit over here, then we perform that growth 80 times over, then what we get is a vector too large to deal with. It might become too big of a number to represent. So that's the problem of something called exploding gradients, where you have a vector of a size. If you keep adding to it in length, it becomes too big to deal with. And the same thing can happen if the vector we start out with is too small. What can happen is that over time, it becomes so small that effectively our computers can only represent the numbers inside of the vector as 0. So what we get is a 0 vector, and 0 represents nothing. So in both of these scenarios, we lose the original meaning that we had in the vector. So we want all of these vectors to be of the same size throughout the entire process. And this process of getting all the vectors to the same length is called normalization. And in machine learning, there are multiple different ways of doing this. In LLama3, we use a specific type of normalization called root mean squared normalization. What this means is, yes, we adjust the vector's length down so that it's the same length as all the other vectors. But another thing that we found advantageous in other areas of machine learning is that if we multiply all the numbers inside of the vector by the same number, then we would still want that to have the same meaning. So if we make the vector's length this long, we want it to have the same meaning as if it was this long. And this is called scaling invariance. And the RMS part of the normalization ensures that it's scale invariant so that the vector doesn't lose its meaning no matter how long we make it, how much we multiply the vector's numbers by. So that's the RMS normalization step. Over half of the steps in a layer are mainly just normalization after normalization, that 80 times over, because it's very easy for a vector to get very large in a very few number of operations. So that's why a lot of these steps will just be normalizing the vector back down to its original size. That's RMS normalization. So we have vectors and they're all of the same length now, so we don't have to be afraid that they lose their meaning when they get too big or small. Then we can start performing the key essential operation, which sets large language models apart from most other types of machine learning models, and that's called attention. Now, LLama3 uses a specific form of attention called grouped multi-head attention. What that means is that the multi-head part refers to how we perform an operation called attention multiple times, and each time we perform it, we call that an attention head. And the group part refers to the fact that some of the calculations can be carried over from one head to another. So we group the heads. The calculations that can be carried over, we only perform them once in one group. In LLama3's smallest model, that would mean we have 8 groups, and in each group we have 4 heads. Now, more specifically speaking, attention is where we have one query. Now, the best way to imagine this is that each word poses a question for the other words. So each word vector we have over here generates a question for the other words to answer, a query. And what we do is we take all the other words, and all the other words generate a key and a value. The key is basically the word saying whether its answer is relevant or not. Each word gives an answer, that's the value. The key is how relevant to the question the answer that it provides is. What we do is we get the query given by the first word, we compare it to the keys of all the different other words, and the closer the query is to the key, the thing that we're looking for, the more emphasis we place on the other word's answer. So we take one word, we make a query out of it, we compare it with all the other words' keys, and based on that, we weight the different values of the words, the different values or answers that the words provided. We add them together, and that's the result that comes out. Now, what machine learning scientists realized was that it's a waste to recalculate the keys and values for every single head because we perform this operation multiple different times. The best way to think about that would be to consider multiple different people looking at the same set of words from a different perspective. So we do that 32 times. Overall, we have 32 heads. And we group these heads so that we can reuse the values and the keys, because it turns out that it takes a lot of computational power to perform this operation I just described to you 32 times. And the hardest part is generating the queries, keys, and values. So what machine learning scientists proposed was that we only generate the queries for every single head, and we reuse the keys and values. So that's what group multi-head attention is. We group the heads, and each group gets only one set of keys and values. And in each group, we have a lot of heads, and each head performs this operation called attention, where we take a question posed by a word for the other words, and we check how much attention in regard to this query we have to pay to the answers the words provided in the text. So to expand on this further, say we have the question, the man walked down the street, and when we're performing attention, we would take the word man, and that would generate a query, which would be something like, what is the meaning of man in relationship to every single other word in this sentence? And then we pay attention to the amount of meaning different words add differently. So for example, the word the, that's a very common word. It doesn't really have that much of a meaning, so we wouldn't pay that much attention to that. Whereas street, the man walked down the street might have very important meaning in relationship to man. Then we would scale up the value that the word street provided for us. So after we had performed this operation, we take the original vectors we had and add it to the original vectors. So we go through the normalization and then the grouped multi-head attention. And this is only just a change we apply to the original meaning of the vectors. This isn't the new set of vectors. This is just a change that we applied in our first few operations. And then what we do is we take this change and then we add it to our original vectors. So now we have a new set of vectors. Then we renormalize them, because after all of this, they may have had slight difference in their length. So we have to get their lengths back into the acceptable range. And then after that, we apply this operation called a gated linear unit to them. What a gated linear unit does is it takes in a vector and then splits it into two branches. We have a gate. So we take the vector, we generate a gate vector out of it, and then we generate another vector out of it. And you could think of this as two different aspects of the original vector. And what we do is we take these vectors and multiply them together. And by that I don't mean any fancy dot product or inner product operation. I literally mean we take the numbers of one vector and multiply it together by the appropriate relevant number in the other vector. So we form pairs out of the numbers. We put the list of numbers side by side. We form pairs out of them and we multiply those pair of numbers. That's how we get the next vector. Then we get this vector, we perform another conversion operation, which is actually something called a matrix multiplication, which I won't get into detail about. And that's the result we get over here. And again, this is just a change we applied to the original vectors over here. So we perform an addition, where we take the meaning of the words we had over here, we add the change to it to get a new word. We perform this around 80 more times, depending on the size of your large language model. You can have 1 billion parameter models, which tend to have around 16 layers, and 70 billion parameter models, or 400 billion parameter models, both of which tend to have around 80 layers. So we perform this operation 80 times. Then, which didn't fit in, then we renormalize the result, because it's good to have all the vectors of the same length. So we perform another normalization over here. Then we unembed the vectors. So we take all the different numbers representing different meanings of a word, or different aspects of the meaning of a word. We convert it back into one number. That's the closest word we can think of that represents best the meaning. Because what embedding is we have a list of words we know, and for each word we have a list of numbers which represent its meaning. And over here, it's not necessarily guaranteed that we're going to have a precise match to one of the words in our massive table of words. So we have to compare the meaning that we get over here to every single meaning that we had over here for all the words we knew. Then we take the closest word to what we think is the answer, then that's our output token. And we expand this single number now, which is representing a single word or phrase, back into text, and then that extra text gets added onto the text you originally provided, and that's the output of the model. There are cases where you don't just want to generate one word, however, you want to keep on going until you reach something called an end of sequence token, which is basically the model saying, I had enough of speaking, these are all the words I have to say about this topic. So that's the meaning of this token. And in that case, we don't detokenize, we just keep on going. We get the output token, the output word, and then we re-embed it and make it go through the entire system again. Then we get another word, and then we do that again. And we do that until we reach the end of sequence token, until that's the token that comes out over here, which is the model saying to us, this is all it had to say based on the input sequence we provided back over here. That would be all I have to say.